Hello and welcome to Ikasan Online Tutorials. My name is Michael Stewart and I'm a core developer on the Ikasan Enterprise Integration and Scheduler platform. And today I'm going to be talking about some of the core concepts of the Ikasan Enterprise Scheduler platform. So what is the Ikasan Enterprise Scheduler? The Ikasan Enterprise Scheduler provides enterprise-grade scheduling services. An enterprise scheduler is a software tool or system that helps manage and automate the scheduling tasks, processes, or events within a large organization or enterprise. It coordinates and organizes various activities, resources, and dependencies to ensure that tasks are executed efficiently and on time. The Ikasan Enterprise Scheduler provides a centralized platform for creating, managing, and monitoring schedules across different departments or teams within an organization. The key functions of an enterprise scheduler include creating and editing schedules, defining dependencies and relationships between tasks, allocating resources, setting priorities, and assigning tasks to appropriate team members. It may also incorporate features such as notifications, alerts, and reporting to keep stakeholders informed about the progress and status of schedule activities. The Ikasan Enterprise Scheduler plays a critical role in optimizing workflow efficiency, reducing manual effort, improving coordination among teams, and ensuring that tasks are completed in a timely and organized manner. It is a powerful tool that helps businesses efficiently manage their resources, optimize scheduling processes, and ensure smooth operation across the organization. To monitor job statuses, the Ikasan Enterprise Scheduler receives real-time job events from agents whose role it is to execute scheduled jobs within a business domain. The scheduler also notifies users or alerts to inform relevant stakeholders about changes in job statuses. External teams can also query job and job plan statuses via services exposed by the Enterprise Scheduler. The job status can be represented by different states, such as queued, running, completed, or error, and the scheduler keeps track of those states for each job. When a job is queued, it means it's waiting to be executed. When it is running, it means it is currently being processed. When it is completed, it means it has finished successfully. And when it has failed, it means it has encountered an error or an issue during execution. The Enterprise Scheduler also provides additional information related to the job, such as the job start time, the end time, the duration, and any other relevant output or error messages. The information provides system operators and developers with an overview of what's happened within that particular job plan or schedule. Now moving on to the Ikasan Enterprise Scheduler architecture. The Ikasan Enterprise Scheduler is a distributed software system. It comprises two distinct software elements: the Ikasan Enterprise Scheduler dashboard and the Ikasan Enterprise Scheduler agent. The Ikasan Enterprise Scheduler dashboard provides management and orchestration features, and the Ikasan Enterprise Scheduler agent executes jobs and reports their state back to the dashboard. The Ikasan Enterprise Scheduler is capable of running in both on-prem and cloud environments, or in a hybrid on-prem cloud environment. Now, the Ikasan Enterprise Scheduler is a distributed software system. A distributed software system is a collection of interconnected software components or applications that work together as a unified system to perform tasks or deliver services. Unlike traditional monolithic or centralized systems, where all the processing happens on a single server or computer, a distributed software system splits the workload among multiple nodes, which can be geographically dispersed, interconnected through a network. In a distributed software system, each node or server operates independently and communicates with other nodes to exchange data, share resources, and collaborate on tasks. The system's architecture is designed to distribute the processing and computing across various nodes and offers several benefits, including scalability, Distributed systems can easily accommodate increasing demand by adding more nodes to handle the workload, allowing for horizontal scaling. Fault tolerance. Due to the decentralized nature of distributed systems, they can continue to function even if some nodes fail or become unavailable, reducing the risk of system downtime. Performance. By distributing tasks across multiple nodes, distributed systems can achieve higher processing speeds and improve overall performance. And flexibility. Distributed components of the system can be developed and updated independently, making it easier to adapt and evolve the system over time. As previously mentioned, the Ikasan Enterprise Scheduler architecture comprises two distinct software elements. The first is the Ikasan Enterprise Scheduler dashboard. And the dashboard is at the heart of the Ikasan Enterprise Scheduler and fulfills the following functions. It provides features that allow for job plans to be managed. It provides features and services that allow for job plan instances to be monitored. It acts as an orchestration engine for all job plan instances. It manages the life cycle of all job plan instances. It provides features and services that allow job plans to be provisioned. It provides services that allow job plans to be exported. And it provides services allowing for job plans and their underlying queuing technology to be monitored. Secondly, there's the Ikasan Enterprise Scheduler agent. The agent will be numerous within a deployment of the Ikasan Enterprise Scheduler, and each agent instance fulfills the following functions. It provides a set of services that allow for scheduler jobs to be provisioned on the agent. It executes the above-mentioned jobs and reports the state of the jobs back to the scheduler dashboard. It receives initiation events from the dashboard in order to execute jobs. And it performs housekeeping of logs created by those jobs. And on to the Ikasan Enterprise Scheduler dashboard. The Ikasan Enterprise Scheduler dashboard is a Spring Boot web application. It provides management and monitoring capabilities for all scheduler-related features. These features include job plan template management, job plan instance monitoring and management, scheduler agent monitoring and management, LDAP integration, security management, core Ikasan services, including the hospital service, the replay service, the wiretap service, the configuration service, and the mapping service. Various REST services related to scheduler features, including features to allow for job plans to be provisioned, as well as other services that support the inter-process communications between the scheduler dashboard and agents. And it also has a context machine cache, managing access to all running job plan instances. The Ikasan Enterprise Scheduler dashboard also delegates to the following software elements to provide the following features. Solar, providing scheduler artifact persistence, indexing and search features. H2, providing relational persistence of dashboard security features. And BigQ, which provides disk backend messaging persistence, providing reliable inter-process communications between the scheduler dashboard and the scheduler agents. So the Ikasan Enterprise Scheduler agent is a standard Ikasan Enterprise Service Bus module that has been extended to provide no-code features to the Ikasan platform. It supports 3 job types: schedule-based jobs, which fire at a point in time and raise an event to the scheduler dashboard at that point in time. File watcher jobs, which monitor a directory and raise an event to the scheduler dashboard when a file arrives. And command execution jobs that execute native commands on the server that the agent installs, monitors the process created, and provides results of the command execution to the scheduler dashboard when the command is complete. The The Ikasan Enterprise Scheduler agent maintains an internal job plan instance cache that contains a reference to all the running job plan instances that the agent is executing jobs on behalf of. It also has REST services exposed that provide management interfaces as well as services that support inter-process communication between the scheduler dashboard and the agent. The Ikasan Enterprise Scheduler agent also delegates to the following software elements to provide the following features. H2, which provides relational persistence of the agent security features, and BigQ, which provides disk-backed messaging and persistence, providing reliable inter-process communication between the scheduler dashboard and the scheduler agents. So what is no-code? No-code, also known as zero code, refers to a software development approach that allows users to create applications or software solutions without writing traditional programming code. Instead of manually writing lines of code, no-code platforms provide visual interfaces and pre-built components that users can use to define, customize, and assemble applications through drag and drop or other simple interactions. The no-code movement aims to democratize software development and make it accessible to individuals with little or no programming experience. With no-code platforms, people from various backgrounds, including business analysts, subject matter experts, and non-technical users, can participate in creating software solutions for their specific needs. Key characteristics of no-code platforms include visual development, in which users can define or design applications by arranging visual components and defining their behaviors through graphical interfaces, eliminating the need for writing manual code. Pre-built components, where no-code platforms often come with a library of pre-built components and templates that users can customize to suit their requirements. Integration capabilities. No-code platforms usually offer integration options to connect with other systems, databases, or APIs without requiring custom code. Rapid prototyping. With the simplicity of no-code development, users can quickly create prototypes and iterate on their applications. And they're user-friendly. No-code tools are designed to be user-friendly, making them accessible to individuals with diverse technical backgrounds. So how does the Ikasan Enterprise Scheduler platform achieve no-code? So job plan templates are managed from within this Ikasan Scheduler dashboard, and these job plans define how a group of jobs are to be executed and how they relate to one another. Once a user has completed a job plan in the Ikasan Scheduler dashboard, the jobs are provisioned onto the relevant agents. The agent is deactivated and a set of configurations are provided to it. Once the agent is reactivated, all of those jobs are configured on that agent, and that agent is ready to perform the job plan for which it has been provisioned. What is a job plan? A job plan is a JSON document that describes how a group of jobs and nested job plans relate to one another in order to provide the orchestration of a complex set of business processes. It is modeled as an node and edge graph with logical structures that define the way that the jobs relate to one another. It is the template for the creation of job plan instances. A job plan instance is an active job plan. It has a temporal nature to it that is governed by the cron expression that tells it when to start, as well as a time to live value that defines how long the job plan instance will remain active. Users can interact with the job plan instance via the Ikasan Enterprise Scheduler dashboard and can perform actions such as skipping or holding jobs. They can also monitor the status of the job plan instance and jobs as jobs are executed within the job plan instance. What is a context machine? The context machine is at the core of the Ikasan Scheduler. There is an individual context machine created for each job plan instance. The context machine is responsible for managing a job plan instance It does this by listening for scheduler events and applying logic against the job plan instance to determine if there are any jobs that can be initiated as a result of a scheduler event received. If there are, the context machine notifies any agents of those job initiations. As each event is received, a state change occurs against the underlying job plan instance, and the job plan instance is updated and persisted, as well as there being an audit record created for each transition in order to provide complete transparency and auditability of the behavior of the Ikasan scheduler. Okay, just to elaborate a little bit further on the way the context machine works, here's a state diagram that represents the various transitions that a context machine goes through when it receives an event from an agent. So the scheduled process event is received, and the context machine processes that event. The way that it processes the event is by recursively working through the underlying job plan instance and marking the job for whom the process event has been received as the state that's been received within that event, and assuming that that job has been successful, the context machine determines if there are any jobs to initiate. Once that event is processed, the state of the job plan instance is updated and subsequently persisted into the database, and a set of audit records are created and persisted to the database as well. And now, back to when we were processing the event, have we determined that some jobs can be initiated on the back of that event received? The answer being yes. We notify the agent that those jobs can now be executed. If not, the context machine has reached its end state and there's nothing to do. So if we have notified an agent that there are jobs to do, those jobs will subsequently be processed by the agent, and when they're complete, the agent will notify the context machine again of the completion of those events and their state, and this state machine or this state diagram will begin from the begin node again with the receipt of a process event, and will process that simple set of steps again to determine whether more jobs can run. Now, just to elaborate on that a little bit further, so we've seen how the context machine processes an inbound schedule event. This next slide is going to show us how the Enterprise Scheduler dashboard subsequently communicates with the agent in order to notify the agent that it can perform a job, and how it does that in a reliable and fail-safe manner. So once the context machine has processed an inbound contextualized scheduled process event, it will have determined if there are any job initiation events that need to be raised to any agents. Each of the job initiation events are placed onto the dashboard outbound queue. A process within the Ikasan Enterprise Scheduler dashboard then reads each message on the outbound queue and publishes them over a REST call to the relevant agent. The outbound process implements various retry and fail-safe algorithms in order to guarantee the delivery of the job initiation event to the relevant agent. A REST inbound service on the agent determines which job that the job initiation event is required to run, and publishes a job initiation event to the relevant inbound queue. The target command execution job reads the job initiation event from its dedicated inbound queue and executes the job. The job initiation event contains all information necessary for the job to execute, while any job plan instance data required, such as job parameters, can be read from the job plan instance held in the job plan instance cache on the agent. The Ikasan Enterprise Scheduler dashboard is notified when the job starts. When the job completes, a contextualized scheduled process event is created in order to notify the dashboard of the outcome of the job. All of this is done in a reliable manner. There's various algorithms implemented to guarantee the delivery of events from the dashboard to the agent. Now, the agent also needs to communicate the state of jobs back to the dashboard, and it fulfills that role in a very similar way with reliability gained by having some outbound and inbound queues on both the agent and the dashboard side. Now, there are three various job types that are executed on the agent. So there's a scheduled job, which basically fires at a point in time. There's a file watcher job, which determines the arrival of a file and notifies the scheduler dashboard that file has arrived. And we've already seen that there's a command execution job, which is executed when the context machine initiates that event. So both the file watcher and the scheduled jobs need some context. So they reach into the job plan instance cache and they get details of the instance for which they're firing on behalf of. So when they enrich their job plan, their scheduled process event, they provide that context instance identifier in that event, and that gets fired to the context machine via this mechanism we're looking at here. So job plan instance identifiers are provided to schedule and file watcher jobs in order to correlate the event published to the dashboard with the appropriate job plan instance managed by the dashboard. Contextualized scheduled process events are published to the agent outbound big queue on the file system of the agent host. The agent outbound flow consumes the contextualized process events from the agent outbound queue and publishes them to an inbound REST service on the Ikasan Enterprise Scheduler dashboard, which in turn places those messages onto the dashboard inbound queue. An inbound flow that consumes a contextualized scheduled process event from the inbound queue. The context machine that is managing the job plan instance is resolved using the job plan instance ID contained in the inbound contextualized scheduled process event. The event is passed to the context machine to be processed in order to determine if any jobs can be initiated upon receipt of that event. The job plan instance's state is updated and persisted with relevant order event details. So you can see we're starting to see the big picture here, how the context machine is processing inbound events, how it's creating initiation events, and how it's publishing those events back to the agent in order for the agent to execute the jobs. We've got a full end-to-end cycle there now of how the context machine at the core of the Ikasan Enterprise Scheduler is orchestrating a job plan in combination with agents executing the jobs. So the next concept we're going to be looking at is the job plan lifecycle. So why is a job plan lifecycle necessary? Well, Ikasan employs a distributed microservice architecture, with which comes many benefits such as a highly decoupled system, robustness, resiliency, scalability, and reliability. However, a distributed system is also burdened with more complexity due to the following. Nodes in the architecture may need to send state to one another, and nodes may need to adhere to certain startup and shutdown protocols in order to make sure that data integrity is maintained. More specifically, the Ikasan Scheduler has some challenges relating to job plan instances and the way that details of job plan instances such as parameters are shared between dashboard and its agents. This is even more exaggerated by the fact that two of the Ikasan job types, being the quartz schedule-driven jobs and the file watcher jobs, are completely decoupled from the life cycle of the underlying job plan from which they are being executed. That is, each of those job types need to be told of the context instance identifier or the job plan instance identifier that they are firing on behalf of. And that allows the orchestration engine or the context machine in the dashboard to associate the events that are received with the correct job plan instance. In order for a job plan instance to be managed within a life cycle, there are a number of states that are associated with that job plan instance. In it is important to understand what those states are in order to understand how this life cycle is fulfilled. We have a number of states that the job plan instance can be in. So a prepared state is a job plan instance that is in a prepared state, has been created and will be moved to a waiting state and become active when the job plan time window start cron expression fires. So that means that the job plan instance has been stood up and is ready for its start time to occur. That allows users to interact with the job plan and do some work against certain jobs. Perhaps jobs need to be put on hold or skipped prior to that job plan instance starting. Now, once that time window start cron expression fires, job plan instance moves from a prepared state to a waiting state. Now, when a job plan instance is in a waiting state, it has not received any events yet, and it is ready and waiting to receive events so that it can start to perform its underlying job plan that it's managing. Once events get received, a job plan instance moves into a running state. So a job plan instance that is in a running state is now active, and some jobs within the plan are either running or are complete. There have been no errors within the job plan instance, but some jobs are still waiting. So just an overview there, that a job plan that's running or job plan instance that is running can be considered to be in a healthy state. There are no errors, there are no concerns, it just has not completed yet. Moving on to the complete state. So a job plan instance that is in a complete state is now active, and all logical job groupings within that job plan instance are considered to be complete. Given that it is in the complete state, we consider there have been no errors and everything's been completed successfully. Now, moving on to the error state, a job plan instance that is in an error state has at least one job within the job plan instance that has errored. Other jobs within the plan may be complete, running, or waiting, but the error wraps up to the job plan instance state. So it gives us full visibility at the parent level if there are any jobs within that job plan instance that have errored. And finally, we've got the ended state. A job plan instance that is ended has exceeded the context time to live millisecond configuration value. And that's from when it first started. The job plan is no longer considered active, or the job plan instance is no longer considered active, and the context machine will no longer interact with it. There are three main use cases associated with the job plan instance lifecycle. The first use case is the most simple one, and that is simply a job plan registering itself with the internal scheduling engine of the Ikasan Scheduler dashboard and telling it that a job plan instance should be stood up at a point in time in the future. Now, that job plan instance can be registered when the job plan is enabled, or it may be registered at the point in time that the Ikasan Scheduler dashboard starts up. If we start on the left-hand side there at our start node, we can see that job plan is registered with the Ikasan Scheduler dashboard to fire at a time that's associated with the start time window cron expression. So as we move on, that cron expression fires, and then the job plan instance goes through a series of states. So the first thing that happens is we determine if there's a job plan instance already in a prepared state for the job plan that is firing on that cron expression start time window. And if there is one in a prepared state, it is moved to a waiting state. That job plan is then considered active. If there isn't one that's in a prepared state, a new job plan instance is created and set to the waiting state and is added to the job plan instance cache. The context parameter factory creates all job plan parameters, and there may be some moving date values or something like that that need to be configured and set on the job plan instance, and that is the point in time at which that is done. All scheduler agents that participate in that particular job plan are notified of the new job plan instance, and they receive the associated job plan parameters. And finally, a new job plan instance is created and its state set to prepared, and it is added to the job context instance cache. The second use case associated with the job plan instance lifecycle is associated with the dashboard restart, where we have running job plans that need to be recovered in order to allow them to continue to process the events associated with that job plan instance. So we go to the left-hand side, we look at our start node, we can see the first thing we do is we load all of the job plan instances that are in the following states. We load the waiting, running, error, complete, and prepared job plan instances. The first thing we do is we determine whether any of the prepared job plan instances should have started while the dashboard was stopped. If that is the case, and there are some, we take each of those prepared job plan instances and we mark them as waiting, and we add those job plan instances to the context machine cache. We also create a new prepared job plan instance for each of those, and we put that into a prepared state, and that also goes into the job plan instance cache. The next thing we do is we determine whether any of the active job plan instances should have ended when the dashboard was down. If that is the case, that we do have some, we mark those job plan instances as ended, and we move on to loading all of the job plan templates that are enabled. What we need to do now is determine whether the running job plan instances that we have are the complete set of job plan templates that are enabled and should be running. And we determine if there are any that are missing, we need to stand up a job plan instance for each of those, put it into a waiting state, set up the context parameters for it, and add it to the context machine cache. Now, once all of that is done, all of the running job plan instances are published to all of their relevant agents so that they're now in sync with those job plan instances and can continue to process. Once all of that is complete, we've achieved that outcome, and the dashboard restart is now synchronized with the entire scheduler estate, and the job plan lifecycle has been adhered to. The third and final use case in the job plan lifecycle is the situation where an agent restart occurs. So an agent restart, we need to go and request from the dashboard all of the current running job plan instances, configure the relevant jobs on the agent with the job plan instance IDs so that the appropriate event identifier gets fired into the dashboard when a particular job is executed. And then we need to put those job plans into the local job plan instant cache so that they can be referenced for things such as configuration parameters or any other information that a job needs to execute a specific job out of a job plan. So you can see here, we start on the left-hand side, the agent restart occurs. So the first thing that happens is we make a REST call to the dashboard, and that REST call is requesting all of the current running job plan instances that are relevant for this agent. We retry if we're unsuccessful. Assuming that we've been successful, we go ahead and configure all of the quartz or scheduler jobs and the file watcher jobs on the agent with the relevant job plan instance identifiers. And then once we've successfully reconfigured all of those jobs, we go ahead and we put all of those job plan instances into the local cache, and they're available for any jobs that may need to use data from that particular job plan instance to enrich any of the contents of that job. Once we're done there, we've reached our end state and the agent restart has been successful. Well, thank you very much for tuning in to Ikasan Online Tutorials. If you'd like further information on the Ikasan Enterprise Integration Platform, go to github.com/ikasaneip. That's lowercase ikasan uppercase EIP. All the links will be in the descriptions of the videos associated with the Ikasan Online Tutorials. And if you've liked what you've seen today, please subscribe to the Ikasan Online Tutorial YouTube channel. We'll see you next time.